the square root in there. If you don't have the square root and you're stuck, then you should be thinking, is there a way I could rewrite this as a square root? Right? Could I? And then you try. All right, let's keep going. I'm going to go ahead and get the answer for this part. And I'll put the work up here just in case. U is x squared plus 1. du is 2x dx. I don't have to do anything with this because I've got it exactly. So that integral is going to be 1/2 1 over u squared, which is u to the negative 2 du. So that's what that does here. The antiderivative of that is negative u to the negative 1. So the answer to the first part, negative 1/2 u, but u is really x squared plus 1 to the negative 1. So that's the antiderivative of the first one. Okay, so that one's done. I don't have to worry about that anymore. This one over here, I'm going to go work on. All right? So I'll put plus here, and then I'll put question mark. All right, let's go do this one. So I'll come back to that. All right, here comes my trig sub here. I'm going to let x equal what? A tangent theta. So just tan theta. And from last class, we learned that on your formula sheet, oh, you know, so I was driving to work today, and I was like, yeah, I think I'm going to give my Cal 2 classic quiz today, right? And I was like, I'm going to make it a pretty simple trig sub problem, and I'm going to see who doesn't bring their formula sheets. And then they're going to be, I don't have my sheet, and I'm going to have to tell them you're not prepared. So that didn't happen. I didn't give you the quiz, but the moral of the story is you better have the formula sheet. If you don't have it memorized now, you better have your formula sheet. So make sure you bring it with you. What does this turn into? A secant theta. So in this case, just secant theta. And then what is dx? Secant squared theta d theta. So this is all from last class. We said when we do a trig sub, we're going to have 3 important elements. Here are the 3 important elements for this particular trig sub. And then we rewrite it, right? So this integral is going to become integral 1 over, the root is secant theta, right? To the 4th power. So secant to the 4th theta. And don't forget the all-important dx. And this happens a lot in tests. Students will leave out the dx. And if you leave out the dx, man, this integral is something completely different. What is dx for us? Secant squared theta, d theta.
So doesn't that just become 1 over secant?
This becomes, the secant squared cancels here. We get that 4 to become a 2, so that's 1 over secant squared, which is actually just cosine squared. And we're not afraid of cosine squared anymore. We used to be. But we were afraid of it until we realized we had the power reducing formula, right? Yeah, so now this is just 1/2, which I'll pull out of the integral. And then we have 1 plus cosine 2 theta d theta. I think you are really starting to kind of appreciate the fact that your next test is going to have 5 questions on it, right? Like are you getting it now? Are you getting it? I mean, like, anything over 5 questions would be unreasonable in terms of time.
Yeah.
But one question will incorporate every technique, you know, is built in almost, right? And that's why I've also said if you can do well on exam 2, then whatever anomaly may have occurred for you in exam 1, I'm going to look at with a little less scrutiny. Does that make sense? Like if you do well on exam 2, like that means you've come far away from exam 1. Can you also appreciate why I don't give you an exam 2, like an exam 1 after all these techniques? Like one exam that's going to cover, yeah, I mean, it's overwhelming. All right, but okay, shut up. Let me just finish this. All right, now what?
Now we have to take the
Antiderivative, right? I still need the antiderivative. So we have 1/2, and then we have antiderivative of 1 theta plus antiderivative of cosine 2 theta. 1/2 sine 2 theta plus a constant. I need to know what theta is, and I need to know what sine of 2 theta is. I'm going to need a triangle. Yeah, we have done this before. Y'all know what's going to happen with this, right? You're going to have to use that double angle identity to get that to be 2 sine theta cosine theta, and the 2 is going to cancel with the half. Okay, so we've played this game. All right, I still need my triangle. Let me go back up here to my triangle. Do I even need the triangle? Who cares? I'm going to do it anyway because it's just so much fun. There we go. There we go. That's my triangle. That comes off of this information. Tangent theta is x, which is the same as x over 1. So tangent is opposite over adjacent. Then you can solve for the third side. So if anyone asks me for any information about theta in terms of the different trig functions, I've got it now. So first thing I need to know is what's theta? What is theta? How are you going to get theta? You take this one right here and do arctan on both sides. So arctangent of x equals theta. So I've got that. And I need sine 2 theta. I guess I'll do it right here. 1/2, okay, arctangent of x, that's theta. And then plus, since I did this last class, can we all be okay with the idea that that right there, everything I've circled, is just sine theta cosine theta?
Yes.
Okay, that's sine theta cosine theta. Put it right here. That's sine theta cosine theta because the 2's cancel. The half and the 2 cancel. Now, what is sine theta? X over this, right? X over root x squared plus 1 times what's cosine theta? 1 over that root. Okay, that's the antiderivative of this right here. Right? Antiderivative of this, all that is this. And that's what I still needed to throw into my answer. So we're there, folks. I'll need a plus c at the end of all this. But, okay, let me put this together. I'm going to pass the half through here. So I'm going to have a half of a tangent inverse of an x. And then I'm going to have another half. And then this one is going to become x over x squared plus 1 plus c. Y'all see what I did there? Those two, I multiplied those two fractions together. I put these together, that was x up top, and since these were the same, the roots go away. Wow.
How is that 1/2 sine 2 theta, sine theta cosine theta? That's like the only thing I'm like.
Well, sine 2 theta is a trigonometric identity from pre-cal. Sine 2 theta in pre-cal, we learned that sine 2x is equal to 2 cosine x sine x, or you can do it the other way around. Sine x cosine x doesn't matter, it's multiplication. So this is from pre-cal. And because of that, I replaced that with that, and then the 2 and the half cancel. And so, you know, when that cancels, then you just get the cosine theta, sine theta. That should have happened in the homework, or that will happen in the homework if you haven't gotten to it. So you will have, again, theoretically, you will have seen that already, but okay. What was the integral? This was the integral, I forgot what it was. X plus 1 over
X squared plus 1 squared.
Okay. That was the original problem, right? That's the answer?
Yes.
I'm going to check it. I'm going to check my answer. Are you ready? Here it comes. I'm going to check it. Here we go. Negative 1 comes out, right? That just becomes a positive 1/2. X squared plus 1 to the negative 2 because you subtracted power. Chain rule. Derivative of what's inside, 2x. Okay, those 2's are going to cancel. Plus 1/2 times derivative of arctangent of x, 1 over 1 plus x squared. Plus 1/2 quotient rule. Derivative of the top times the bottom. Minus derivative of the bottom times the top. All over bottom squared. Right? Okay. Let me clean that up. This is 1/2. All right, here we got x squared plus 1, right? And then minus 2x squared, which really means 1 minus x squared. Yes? Over x squared plus 1 squared. Okay, so that's that part. In front of this, I've got 1/2 1 over 1 plus x squared. And then over here, I've got the 2's that canceled. This is really what? What's my fraction over here? X over, right? We still have this x, so x over x squared plus 1 squared. Yeah? Okay, this right here, I don't need this bracket anymore. That's just multiplication, right? So let me put all those together with a common denominator. Do you agree that this 2 is down here with this? Yeah. This 2 is down here with that? Yeah. And this doesn't have a 2. So my common denominator needs a 2, doesn't it? So that means I better put a 2 here. Even though I just canceled it, I'm putting it right back. And then what do I need for in terms of my other stuff? This has x plus 1 squared. This one does not have it squared. This one has it squared. So I'm going to need this one to be squared. So I'm going to have to introduce it on the top. Multiply 1 plus x squared on the top and the bottom, which does that, right? So now we have all the same denominators. Let me put the numerators together. First numerator is what? 2x. Next numerator? Just that, right? I don't need the parentheses. Okay, plus, remember that 2 is down here. The next numerator is 1 minus x squared all over 2, 1 plus x squared squared. 2's cancel. Oh, yes. There it is. Okay, this and this together are 2. So we have 2x plus 2 over 2, 1 plus x squared squared. And factor 2 out of the top.
Which would be
Right? Factor the 2 out of the top and cancel with this 2. And you get x plus 1 over 1 plus x squared squared.
You ever blow your own mind once you go back? You're like, wow.
I feel like you have
I
a
don't know.
different class, so maybe not.
What? I had a what?
Well, you have another class, don't you?
What about?
Or how to?
Mm-hmm.
So you probably don't blow your own mind. while you
I've been doing this too long.
Yeah,
This
but I mean,
doesn't
like,
blow
when
my
you
mind.
when you first, like,
I don't know. I love this stuff. I mean, I don't know. There's something
A lot
about.
of people laugh. Like I say, like math is weird.
Yeah, I mean, there's something to me that's just. I don't know. It works. Like it worked, right? Like it worked. I don't know. I feel like I have forgotten what it's to be sitting there.
Yeah.
Okay? But I hope that I still present it in a way that it is accessible to you, because there's no denying that this is difficult. There's no denying that there's so much room for error, right? Just if I would have messed up one sign anywhere in that, this would not have worked, right? The only reason I didn't mess it up is because I think I've done it enough And, but do I make mistakes on it? Sure. I mean, yeah. It's important for you to see this done properly. This is the proper way it's done. It's a lot of work. It's a lot of thinking, but, you just have to raise your bar for yourself. Okay. I only check the answers because I get that little euphoria feeling, like yes, that the thing that you get, right? I like it when we check the answer and it works. Well, let's talk a little bit about partial fractions. Maybe we should just take a deep breath.
So what we just did wasn't partial fractions?
No. So that's the setup. So all of that was just the setup. If we see any of those scenarios now, we know we can attack them. Remember, from college algebra, what a rational function is? Well, in case you've forgotten, it's just the ratio of two polynomial functions. So a polynomial is a function that has powers of x, and that the powers can be either like, well, x to the 0, x to the 1, x squared, x cubed. So you can't have any square roots. You can't even have any like weird fractional powers, no negative powers. If you have a polynomial divided by a polynomial, then we have a rational function. Here are some examples of rational functions. Every one of these is a polynomial divided by a polynomial. Right? I have to talk a little bit more about this. I don't know why. I think I said to you all in the beginning that Calculus 2 is, I've talked to a lot of you about what your majors are and what you're going to be doing in real world and stuff. And I've tried to explain, like, you're not going to be doing integration, right? Okay? But can you appreciate what it takes to do this correctly? Like, you have to be meticulous. You have to be able to call on things from different places. You've got to recognize things. These are all characteristics that we're trying to build in your mind. That ability to problem solve and, that's what we want. We don't necessarily care whether or not it's an integral or you trying to figure out how your code needs to work to make your program run the way it needs to run. It's all critical thinking, and it's all being precise. That's what it's about. I mean, I know there's some CS majors, syntax errors in your code, you hunt them down. I mean, it's terrible. It's hard. I mean, it's easier nowadays because the computer can even tell you where your syntax errors are. But, I mean, I don't know. I don't care whether or not you can do an integral in 3 years. I care whether or not you can problem solve, whether or not you can actually apply this sort of thinking to something else. And some colleges want it regardless of your major. They want to weed you out. Okay, so these are all polynomial rational functions, right? These are all rational functions, and we are going to integrate every single one of those. That's going to be what we do by the end of next class. We're going to take the antiderivative of these. And right now, let's just get some appreciation for the fact we can't do it. We can't do anything that we know yet. Like, this right here is not like constant over linear. It's not like, linear over quadratic. It's nothing that we've looked at in the previous 8 examples, and it's nothing we've done before that. So there they are. All right. So how do we go about this? Well, the strategy for integrating rational functions is as follows. The first thing we're going to do is look at the degree of the numerator and compare it to the degree of the denominator. So by degree, we mean the highest power of x. So the degree of the numerator here is what? 3. Degree of the denominator here is 1. Degree of the numerator? 2. Perfect. Perfect. We just have a test on that, right? Okay. All right, so we do that first, right? If the degree of the numerator is less than the degree of the denominator, The top one's smaller than the bottom one. Then we move on to the next step. All right? If the degree of the numerator is bigger than or equal to the degree of the denominator, we must use long division first. So let's go back through these. Am I going to need long division or not? Yes. This is bigger than that. Am I going to need long division or not? No, because that's smaller than that. Do I need long division here? Yes. Long division here? Here? Yes. If they're the same, you need long division. All right? So we do long division first. Or we don't, okay? So here's the next step. For the remaining rational function, so if we've done long division, we're still going to have a rational function left. If we don't do long division, well, we're just going to be looking at the rational function we started with. In either case, we've got some rational function in front of us. Then we are going to use partial fraction decomposition to break down the rest. And the way we do that, well, you remember that from pre-cal? It's a bit messy. And especially when you look at the form, like the notes for it, it can be really somewhat complicated. And I can appreciate this. As a mathematician, I can appreciate the precision in which this is written. And the fact that we use subscripts on the capitals, because what if you have so many terms that you run out of letters in the alphabet? So we subscript stuff so that we never run out of letters. That's mathy, though. That takes away, that kind of clouds what's really going on. So instead, I like to just look at the problem, okay? And as we start to need the partial fraction decomposition, I will do it. And as I do it, I will remind you as to what it is we're doing with partial fractions, all right? So I think we can do this first one, and we've got time, and I think it's going to work out real nice. So let's try this one. First step, do we need long division or not? Yes, we do. So let's do long division. Now, long division, let me remind you, comes from the good old... How did my marker already die? Have I been like sitting here yapping that long? I think I have. Okay, so just remember what this means, like back in the old days, right? 15 divided by 3, you go like this. And I'm not trying to insult your intelligence. I just know some people hate long division. And it's not as bad as I think you're making it out in your own mind. Okay, so that's what 15 divided by 3 means, right? So then what you ask yourself is, what do I multiply 3 by to get 15?
5.
So you said 5, right? And then you could say 5 times 3, right? You multiply this times this, and you put it here. And that's 15, right? And then what do? You were to subtract that. And when you subtract, you get 0. Does that look familiar? And if you get 0, then your remainder is 0. And your answer is 5, right? Got it? So this is just 5. Now, if we do 15 divided by 4, things are a little different. We go 15 here, 4 here, and we say, what do I multiply 4 to get 15? And there's not a number, right? So we try and get as close as we can without going over. So 3. So we put 3 here, then we go 3 times 4, right? And that gives us 12. And then we subtract, and that gives us a 3 here. And then we ask ourselves, what do I multiply 4 by to get 3? And this is bigger than this, right? So you can't. So you stop, and this is your remainder, right? So you put that little R3. Now you're like in 3rd grade, right? We don't use R3, right, in math. What we do instead is we say 3 plus the remainder over the divisor. So 3, and then plus whatever our remainder is, divided by whatever the divisor was, right? Okay. All long division is this same process with the polynomials in there instead of the numbers. Okay, so let's do this one. I mean, that's all it is. I'm not trying to make it out to be that simple. There are some complications. For example, in this particular problem, we have x cubed plus x. That goes inside the box, right? And you have to be careful because you don't have an x squared in here, right? But you could have an x squared within your answer. So we usually put like a space there for the x squared. We can just put like 0x squared. That just gives us a nice column to work with in case we need to. And then on the outside, we put the divisor. x minus 1. We put it in descending order, highest power of x down. Same with this. And then just like we did with the 4 and the 15, we say, hey, what do I multiply? And you don't look at the whole thing, you just look at x. What do I multiply x by to just get that?
X squared.
Just x squared, right?
Yes.
Okay, so you put x squared up here. It doesn't matter where you put it, all right? Some instructors are like, put it above the x squared. It doesn't matter, okay? X squared, there we go. That's like our 3 here, right? Now, what do we do with the 3? 3 times 4 was 12, right? So here, you have to go x squared times both of these, right? So you go x squared times x, that gives me x cubed, and I'm going to put it underneath x cubed. And then x squared times negative 1, so negative x squared, and notice I put that underneath the x squareds. Now I'm going to subtract. So I come in here, this becomes a minus, and this was a minus, so it becomes a plus. And now what I do is I add straight down and see what I get. My x cubes cancel. X squared, I have none of them, right? And I'm adding one of them, so I have x squared here. And then plus an x. This x comes down. And then we play the game again. What do you multiply x by to get x squared? X. So I put x here. And then we do the same thing. X, just this x, times this, then x times that. So what do we get down there? X squared. So I put it under this. And then minus what? X. So I put it under that. Come through and don't forget this. Subtract. This becomes add. And we go again. So down here is nothing. Here is 2x. We play it again. What do you multiply x by to get 2x? 2. So I put a 2 here. Okay, 2. 2 times that, 2 times that. So 2x, and then minus 2. Come through, change the signs, and add down, and you should finally get what down there? 2. Now, what do you multiply x by to get 2? Well, you're done now because you can't turn x into 2, right? So that's your remainder. So what we do out here is we say plus our remainder over our divisor. Agreed? So what is this all saying? This is saying that if you want to do this integral, then you really need to do this integral, because they're the same thing, right? This divided by this is that. So that means I really need to integrate x squared plus x plus 2 plus 2 over x minus 1 dx. And are you happy to see that? Brutal honesty there. Are you happier to see that than that? Yeah, because look, there's a bunch of pluses in here. You can do them term by term. Antiderivative of that, 1/3 x cubed. Antiderivative of that, 1/2 x squared. Antiderivative of that, 2x. Antiderivative of that, 2 natural log absolute value of x minus 1. This is just a constant over a linear expression. See, we did that. It was the first thing we did today. Constant over a linear expression, right? So I don't need to do any more work. I don't even need partial fractions decomposition. This first example did not need it, because the last piece we got, we could do. So the answer to this is 2x. No, what the heck am I doing? I'm integrating. I'm differentiating. 1/3 x cubed plus 1/2 x squared plus 2x plus 2 natural logs of x minus 1. I did not have to scale out anything on this one, did I? Because that was a 1 in front of that. And the 2 just came for the ride. There you go. Okay, so that one did not need partial fractions. When we come back next week, we will start to get into it. So, you have enough work to do, I think, already. I'm not going to add any more, so you don't need to start anything from 6.2. If you want to do anything that might help you, you might just go back and review partial fractions a little bit. I will try my best to kind of reintroduce it, but I'm not going to reteach it. Just like I did here, right? Like I kind of talked through long division, but I'm not going to sit here and give you some formal process for long division. All right. Have a good weekend. I'm letting you go early. Can you believe that?
You want to send these in right now?
What is this one?
You said, I heard something about turning in for 80.
Yeah, you should probably, yeah, I'll just go. Don't worry about it. Y'all are all here. This is that cosine. This is from last time?
Yeah.
Yes, okay.
Just making sure you're looking at me like,
Yeah, no, I forgot about it. I said that the max you could get was like an 80, right? Yeah.
Early?
Let me turn off the camera. That way we're not
You're not.
chit-chatting. Okay, so what?